the curl of f here but now we just convince ourselves that this is equal to in this picture. Okay, I'm saying that the ds vector is yeah, so I'm well, hold on. And what does this mean? This is the z component of the curl, but that's something we already derived. Okay, and at this point it doesn't really matter if you open the book, the back cover, and look at the expression for the curl. You're fine. Okay, so the curl will have an x component, a y component, z component. Just look at the z component of that, and it's going to be something. Don't remember exactly, but it's going to be something like df x dy minus df y dx, something like this. Okay, don't trust me fully on this. I don't want to look, but. And then ds is, of course, the element of area, which is nothing but dx dy, or if you want, just call it a squared, either one. Okay, so this could be dx dy or a squared, either one is fine.
Okay, so it's the opposite.
Okay, so it's the negative? So not bad for a guess. Okay, thank you. Okay, so okay, so we have that for this. So I did this integral, correct? You see, I did, for that small patch, this integral is already what I just wrote, because I have a very tiny, is that clear?
What does ds represent there?
ds is the area of this thing. Well, the scalar. The vector is a vector that points perpendicular to that. Okay? Okay, but I also said that when you are doing an integral on a very tiny patch, then the integral is nothing but the integrand times the patch. Okay? I want you to say yes, please. Yes. But are you sure? Okay, okay. This is nothing but calculus 1, a little bit. Give me 1 second. If I integrate between x and x plus dx, all I do is evaluate the function at x and multiply times dx. The integral, of course, is a little bit more complete, the full thing, if I integrate in a finite interval. But just hold on, second and first.
This one is the result, the last line. This is the result after
yeah, this is the explicit result of multiplying this times that. Okay. So what I'm claiming is that that thing that I just wrote down there is already this part of the Stokes theorem, but applied to a small patch. Yes?
When you say we're taking the integral, like let's say we have the open bottle, are you also accounting for the surface on the inside of the bottle, or just the outside?
Good question. Good question. Yeah. So no. Because in this case, we are just talking about a mathematical surface with only with no thickness. So you just need to integrate on the surface itself. Okay. In a real surface like the bottle, it's a different story. Then you have a volume inside there. No, this is different.
That means wouldn't the inside the normal vectors be pointing in the opposite direction from the outside?
Say,
Meaning on the inside of the bottle, the normal the direction of the s would be pointing the opposite.
yes, yes.
Wouldn't they cancel each other out?
But that's why you don't do that. That's what the theorem says. So exactly. So in this case, you do either out or in, but not both. That's what the theorem states. Yeah, that's a good question. Thin, not a real surface, but a mathematical surface. Okay, and so we did that. Okay, so what about the left-hand side? Okay, how do you do that? Any ideas? Anybody helps me how to do this on that little patch that we consider? What would be this integral? And what do you think is L? Even if it's wrong, or give me an idea. What? The contour, exactly. No, it's not exactly that, but that's at least a good way to start thinking about it. Yeah. So in principle, although it's not completely right, I mean, in fact, it's not right, but it doesn't matter. To get the idea going is good enough that this integral is the field f times the length, and the length is 1, 2, 3, 4, maybe 4a. Okay. Turns out that this is a little bit more difficult than that, but what's that?
It's a line integral?
Exactly, it's a line integral, that's what it is, yes, yeah. And so what you need to do is the following. You divide the path in 4 segments, number 1, number 2, number 3, and number 4. Okay, in each one of them, we'll have a different DL. So for example, for call it path 1 is such that the element of line dl is equal to dx in the x direction. Correct? Okay, and etc. So for example, for path 4, let me do path 4 as an example. Then we have that corresponding DL is going to be equal to what? dy, yes. dy times negative y, etc. So for each one of them, we have that.
What is this a path around? Isn't this an integral of the curve C? Like, is this an integral of the curve C, or is this an integral of the path around the square ds?
Aha, okay. All right. So that's what if you remember how we proved the divergence theorem, okay, you are going to finish the argument. I'm just talking. But to answer your question it's probably easier to answer your question by drawing this picture in 2 dimensions so you see what's going on, okay? So in that, if the curve C is plane, then it looks like this. And then let's suppose that I take the surface S to be the plane itself, the inside. Okay, now I divide that surface in patches, and now it's very easy to see how they look like. And your question is whether the theorem, if I understand you correctly, applies to this picture or to the small patch, right? But so it applies to the big picture, okay? I mean, it should apply to anything, really.
But I don't understand. Is it supposed to apply to S, or is it applying to C?
It's a theorem that tells me that an integral in C is equal to an integral in S.
Right, but I'm just isolating. We're taking the integral of C right now.
Oh.
We're taking the integral of C.
Yes.
So C, why are we using the S? S is not on C or enclosed by C in any way, is it?
Yes, but I already did that. In this patch, okay, say this one here, which in 3 dimensions corresponds to that one, that patch itself has both a curve C and a surface S.
So this C is not the same as the
No.
The C in this integral is not the same as the C in the big picture you drew. The C in the big picture.
Right.
Oh,
So, but I didn't say C here at all, did I? No.
No, but you defined the opening of the bottle or of the surface as C. So
Yes, and that's what I meant. Okay.
So is C that, or is C the perimeter of the square? Or
Okay. Yes, I understand. C in this context is only the opening of the bottle. Okay. But the point is that if I want to prove that that's true, that should work for any combinations of C and S. In particular, it should work when they are very small also.
So the integral of the C for each individual patch of S is going to be equal to the integral of C, the curve around the curve around opening.
No. That's what we need to prove. We haven't proved that.
That's what we're trying to do.
Exactly, yes. Because remember, it's the same idea as in the divergence theorem. The divergence theorem, we had integrals in the volume that added up, that term, but then integrals in the surface that when you took a little box, you had an integral in the surface, but when you went to the next box, because the normals point in different directions, they cancel out. So I want to do the same thing here. Okay, but you are going to do it. I'm just helping you because there is a lot of details here. So the point is that I can, over here, I did the surface integral. So over here, I dealt with this part, but in a small patch. How do you go from this to the surface? Simply by adding up this result. Okay? Yeah.
Because all of the little areas are the force in one direction can be the opposite of the force of the square right next to it. Meaning, like,
For what? For the C.
Right.
Exactly.
Only the outside which is
Yes. That's what I want to. Yes. Yeah. That's basically the idea. Yes. Okay. So again, so this part over here on the right is the surface integral, and I did it on a small patch. To get to the full integral, all you do is to use the Riemann concept that the integral on a surface, in this case it's a two-dimensional object, is simply the sum of the patches. So then this result is immediate, that's no problem. But what about this one? So this one, so you have to go to the little patch here, and you're going to get the following. So like we did before, let's say that you take this point to be x comma y, and this point over here it's going to be x plus dx comma y, and this point over here is going to be x comma y plus dy. Okay, and this y I don't care.
Doesn't it all cancel?
No, very good, but they won't. Because, look, that's the whole thing. So that's why, let's think about this carefully and then you finish up. But what is the field down here? So I want to do the integral. I want to do the integral on that small patch. I want to do the integral on the small patch. On the small c, not the total c, but the small c, okay? And that's going to be equal to the following. So the integral that I'm interested in is f dot dl. So let's do patch 1, patch 2, patch 3, 4, etc. Okay, so for 1, we are going to get the dot product between the field f evaluated at xy dot the dl of path 1, which is dxx. Okay, so I'm going to write that explicitly so you see. So it's going to be f, the field f, evaluated at x and y, dot the dl at path 1, which is dx times x. Okay? Plus three terms, 2, 3, 4. Let me not write because that way we can go faster. So this is equal to, this term is the following. This is a field f that has three components, fx, y, and z, all of them evaluated at xy. Because I'm doing the dot product with the x, the unit vector x, I'm going to pick up the x component of that vector. Okay? So what about if we call that f scalar x component evaluated at xy times dx? Is that a good notation? Okay? I think sometimes in math f sub x stands for the derivative with respect to x. Not sure if that, yeah? It's partial, yeah, but it's clear that this is not what I'm trying to do here. I mean the component. Going from here to here. F is a vector of 3 components. Each component, I'm going to call them fx, fy, fz. But because I'm doing the scalar product with x, which is 1, 0, 0, I just get out only fx and becomes a scalar, right? Okay, then what are the other 3 terms? Okay, let's think. Plus, the second one will be the y component of f, so it's going to be f sub y, evaluated at x plus dx. Correct? So it's going to be f y x plus dx y times dy. So, the question?
No, so it's not a partial derivative, it's just that product. But because the other 2 elements cancel in, so it's just 0, 1, 0.
For the second one, it's 0, 1, 0, exactly. Yeah. Okay. Maybe I'm going a little bit fast, but you just, you know, spend 2 hours on your own, and you know, you can get together, etc., and try to reconstruct the argument. Okay. But so we get that, and then the other 2 terms are going to be the path 3 and 4 will give me negatives because the top one points in the minus x direction and this one points in the minus y direction. Okay, so for that reason, the third term is going to be minus. It's an x component, x, and I'm going to evaluate it at y plus dy. So it's going to be x, comma y plus dy. Dx, and then finally minus, this is fy evaluated at xy times dy. Okay, and then this, so let's collect. So you see how they are not 0, right? Because only because of this little thing they would